Okay, well, let's move on to polar stuff, polar equations. I'm assuming that some of you have probably seen this before because this is one of the sort of somewhat required things in our pre-calculus sequence. So these are polar coordinates. I am probably going to go through this part of it a little faster than I would in a pre-calculus class because, again, it kind of was part of the course requirements for pre-calculus. So anyway, what it is, let's just talk more about what it actually is. So polar coordinates are, it's kind of just a new way to graph or a different way to graph functions using thetas and or basically using angles and radiuses instead. Typically what you might see on a polar graph, it is just really the XY plane. It still is just the normal XY plane. Sometimes though, what they'll put on here is they'll overlay some stuff. Okay, there we go. Got it. Yeah, Desmos does have a polar option. That's true. But for now, I'm just gonna sort of show you like by hand how you would approach this kind of thing. So this is kind of what a polar graph would look like if you Google polar graphs. This is kind of what you'll get. There's a few different variations, but that's really the idea here. Note it's still the XY plane, like I said before. This is still the x-axis right here, and this is still the y-axis right here. We just put these circles on there to kind of help us graph these things. That's the only purpose of the circles, is just to help you graph it. They don't have to be there, and you can graph these things without the circles. All right, so when we talk about graphs in polar form, in Cartesian form, we have this, right? In the normal Cartesian coordinate system, we have we identify a point by its x and y coordinates, right? The x coordinate tells us we go that far horizontally. The y coordinate tells us we go up or down however many, right? In polar coordinates, we identify points by their r values and their theta values. Okay, so these two things together will identify a point on the xy plane. R is the direct distance from the origin. Okay, so in other words, if I'm talking about r equals 3 in some angle, I would just go out 3. This is r equals 3 right here. You see, because it's 1, 2, 3, 1, 2, 3 away from the origin. Okay, this would be like a point out here would have an r value of 1, 2, 3, 4, 5, 6, 7, right? So that's an r value of 7 right there. Everybody see what I'm talking about there with the r value? It's just how far away from the origin it is. Okay. The theta value then is just what we expect when we talk about angles, right? Like in the unit circle. This here, directly here, is to the right, is theta equals 0. This would be theta equals pi over 6. This would be theta equals pi over 3. And this is theta equals pi over 2, and so on, right? This is what we saw in the unit circle. It's basically the same angles that you see in the unit circle. And so if you want to graph a point like those ones in example 1, look at example 1. If I want to graph these 3 points, let's graph 1 pi over 4. Now when I graph stuff in polar form, what I typically do is go with the theta value first, so the second coordinate first. So what does that mean? Well, the second coordinate is telling me that I need to go to the angle of pi over 4 and point in that direction. Where's pi over 4? It's right here, and it's pointing in this direction here, right? That's where pi over 4 is. So go into halfway into quadrant 1, right, and go in that direction. And then with the 1, what is that telling me to do? Just go 1 away from the origin. So if I were to identify that point, it would be right there. This is the point A right here. Everybody see what I'm saying? It's 1 unit away from the origin, and it's at an angle of pi over 4. Okay? For part B, -2, and so we have to also be aware that we can have negative radius values here. We can also have negative angle values. So how do you deal with a negative radius? Well, typically you go to the angle first, like I said. So 3 pi over 2 would take us 3/4 of the way around the circle right there. We would stop right there. Okay, that's 3 pi over 2. But the fact that it's a negative radius, if it was a positive radius, I would just go 2 out and I'd put the dot right there. That would be +2, 3 pi over 2. But since the radius is actually negative, instead of going in the direction of that angle, you actually go in the opposite direction. So I have to actually go up 2 units, and that point right there would be what B is. So again, the idea here is we're just trying to label points right now, and how do we label points that lie on this type of coordinate system when we're dealing with polar coordinates? Okay, so this one we've got a positive radius and a negative angle. You can also have both of them be negative, right? You can have a negative angle and a negative radius. Okay, so for this one, remember that when you have a negative angle, instead of going counterclockwise to get to that angle, you go clockwise. So positive pi over 3 is going to be going, or sorry, negative pi over 3 is going to be going that way, right? Like if I were talking about positive pi over 3, I would go up and stop right there. That's the angle of positive pi over 3. In this case, since it's negative pi over 3, what do? I go here and I stop right there. So that's the angle of negative pi over 3. And then I need to go out 3 units from the origin at that angle. And so, boom, there's that third dot. It's going to go right there. So that's where C lies. Okay, have you guys seen this before? A lot of you have seen this before in your trig class. I'm thinking some of you must have seen this before. Yeah, good. Okay, cool. So hopefully this is a review for a lot of you. If you haven't seen it before, there's plenty of stuff on Khan Academy or whatever if you want to do a quick crash course in graphing polar functions. But again, we are going to go through this section. We'll do a pretty quick crash course in it. But if you want more, yeah, there's all kinds of other stuff you can use. Okay, so that's kind of the idea there, with how you graph it. Then let's see how you might convert, right? Because this is just, it's still, like I said, it's still the XY plane. You can still graph anything that could be graphed in polar form. You could convert it over and graph it in the regular old Cartesian coordinate system as well. So let's take a look at the second example and see. Well, actually, before we do the example here, let's see what the relationship is between these quantities. So suppose I have a point in, say, Cartesian coordinate system, and I want to convert it into polar. So remember that how we identify a point like this in the Cartesian coordinate system is we have just an x value and a y value, right? Simple enough. That means we go out that far. This is the x distance, right? We go out that far, and we go up this far. This is the y distance, right? That identifies that point. Now suppose I wanted to change this over and use polar form instead. Well, in that case, I need the line directly out to the point because that's going to be the r value. And then I also need to know what that theta is, right? And so you can kind of see we get this right triangle situation here. That's why, a lot of this is the Pythagorean theorem and the regular old unit circle stuff. And so from the relationship between the drawing here, we can see that if I want to change the polar form to Cartesian, I can notice just by looking at this graph that x has to be equal to r cosine theta, and that y has to be equal to r sine theta. And again, you can see that because here's the theta. Cosine is defined to be x over r, so the cosine of theta is x over r. You multiply both sides by r, you get x equals r cosine theta. Similar for sine. Okay, and then finally, there's another relationship in here as well. What is the relationship between x, y, and r? Well, that is, in fact, just the Pythagorean theorem itself. X squared plus y squared is equal to r squared. Okay, so these three equations will allow us to change from polar to rectangular. And then further notice there's one other relationship here if you want to sort of go back in the other direction. In fact, actually, the first two are the ones that go from rectangular to polar. Or sorry, polar to rectangular. Polar to rectangular. When I say rectangular, again, that's synonymous with Cartesian. If I say Cartesian coordinate system, it's the same thing as rectangular coordinate system. And then the other relationship that you can see on the graph is this relationship between theta and x and r, right? Theta, x, and y. I mean, theta, x, and y. What is the relationship between those three quantities? Well, that is a tangent relationship, right? The tangent of theta is equal to, the tangent of theta is equal to y over x. So these two equations here are the ones that will allow us to go from rectangular to polar. So this is the conversions that allow us to go from one to the other. Going from polar to rectangular is actually easier. As you can see, all you need to know is what is r and what is theta. Pretty simple. Going from rectangular to polar, there's a couple things you kind of have to worry about there. Like for example, the tangent of theta being y over x. Well, there's multiple angles that have the same tangent, right? In fact, infinitely many. So we got to kind of think about that when we're converting from rectangular to polar. All right, so let's take a look at that second example. This is polar to rectangular. Okay, so, and you can usually tell when you're dealing with a polar defined function, you'll see, a radius and then an angle. The angles are always measured in radians. So when you see an angle measured in radians as that second coordinate, that's a pretty big hint that you're talking about this is a polar point. All right, so for this one, this is the r value here. This is the theta value here. If I want to know what the corresponding x, y values are, x is equal to r cosine theta. So that's 3. Cosine theta is root 3 over 2. So you get 3 root 3 over 2. The y coordinate of that same point then will be r sine theta. And so that's 3. The sine of theta is 1/2. Sine of pi over 6 is 1/2. That gets 3 over 2. So this point here, if I were to identify it in rectangular or Cartesian coordinates, it would be 3 root 3 over 2 as the x coordinate, and then 3/2 as the y coordinate. Okay. And you can kind of see that that seems to make some sense here, because like if I'm talking about an angle that has a radius of 3 and an angle of pi over 6, here's like radius 1, 2, 3. Pi over 6 is a pretty shallow angle. It would be about right there, right? That would be the point. And then you can see that you have to go further on the x, right? So this would be 3 root 3 over 2 on the x to get out to that point, and then you'd only have to go up 1.5. See? But it is the same point, right? Whether you put it as rectangular or polar, it's the same point. Just depends on which coordinate system you're looking at. Okay, so there's that one. Now, if you want to go backwards from change from Cartesian then into polar, then you got to use that other set of conversions. And so take a look at example 3 to do that. So here we're changing a rectangular defined point, minus 3, 3. So again, if you're thinking about what that's going to look like in polar, we would be going 3 to the left, 3 up. That's a point, and we're trying to decide what's that r going to be, right? What's that r, and then what is this theta going to be? That's what we're after. Okay, so to do that, again, we've got that x squared plus y squared equals r squared, right? So we could say minus 3 squared plus 3 squared equals r squared. This is what allows us to find that r. So that's going to be 9 plus 9, that's 18. So r squared is equal to 18. So r is equal to the square root of 18. But that's 9 times 2, so we can rewrite that as 3 root 2. So that's the r value. Then, to find the theta value, we have this other relationship, right? The tangent of theta is equal to y over x. Well, in our problem here, y is 3, x is negative 3, and so what we've actually got is that the tangent of theta is equal to negative 1. Now, this is what I was talking about, where you kind of have to be a little bit careful about what theta you actually choose here, because there's going to be, even on the unit circle, there's 2 angles that have a tangent that's equal to negative 1. But if you remember your unit circle, where is the tangent negative? Tangent is negative in quadrant 2, so that would be right here, and also in quadrant 4. And the 2 angles that have that that tangent would be 3 pi over 4 would be one of them, And then if you go all the way around like that, 7 pi over 4 is another one that has that same tangent, right? 7 pi over 4. And really, if you were to put this in your calculator, the way your calculator would actually evaluate it is it would go this way, and it would say that that angle right there is negative pi over 4, right? But typically, we want to have a positive angle, and then we usually want to restrict theta to be between 0 and 2 pi. So which angle do we really need here? What's the one we want to identify this point? 3 pi over 4. But we want the 3 pi over 4 one. Yeah, that's right. Because look at where the point actually is. It's in quadrant 2, right? The point that we are looking at is in quadrant 2. Since it's in quadrant 2, we have to choose the angle that puts us into quadrant 2. Okay, so we don't want 7 pi over 4. And based on that restriction I was talking about, we don't want negative pi over 4 or negative 5 pi over 4, whatever that other one's going to be. Right? We don't want a negative angle. We want an angle between 0 and 2 pi. So this is the one we want, 3 pi over 4. So this point here in polar form is going to be 3 root 2 for r and 3 pi over 4 for theta. That's the same point then as negative 3, 3. So again, just be careful with that, with this particular relationship right here. That's the one you got to be a bit careful about. Think about where, like if you were to draw this point in a Cartesian coordinate system, what quadrant are you going to lie in, right? And that's going to help you to determine which of the angles you're going to need to satisfy that tan theta equals y over x. Okay? Which also brings us to kind of another interesting point about polar coordinates is that in rectangular coordinates, every single point in the xy plane has a unique way to identify it, right? There's only one way to identify a particular point, any particular point that lies in the xy plane. However, in polar form, there's actually infinitely many ways to identify the exact same point. See what I mean? You can identify the same point infinitely many ways. Like for example, suppose I said, again using the polar graphs, suppose I gave you this point right here. Let's just make it easy. That's radius 3, angle is pi over 4. So 3 and then pi over 4 is the angle. Notice that could also be written as, let's see, how else could we do it? We could put ourselves into quadrant 3, like down here, right, that way. What angle would that be? That would be 5 pi over 4, right? So I could say 5 pi over 4 is the angle. And if I did that, I would make the radius negative, and that would put me into the same exact point as 3 positive pi over 4. You see that? So that's another way to identify the exact same point. I could also use a negative angle if I wanted to. I could say I could use a positive radius and a negative angle, negative 7 pi over 4. Okay, so everybody see what I'm talking about here? You can identify the same point in multiple different ways, in fact, infinitely many ways. You could change this angle by adding 2 pi to it, right? And then you could add 4 pi to it, 6 pi, whatever. So any multiple of 2 pi added to it gets you around to the exact same point. So how do we kind of avoid this problem of having multiple representations of the same point? Well, what we typically do is we try to restrict r to be just a positive number, and we try to restrict theta to be between 0 and 2 pi. Okay, so if we do that, if we make those little restrictions there, then that will result in a unique representation for these points as well. Okay, so just a way to kind of make it so we don't have to worry about these multiple representations. All right, so now let's talk about the graphs of polar curves, because just as with Cartesian coordinates, first in intermediate algebra, or probably basic algebra, right, you first start talking about, like, how do you identify a point? You go this far this way, you go this far this way, there's your point, right? And then you start talking about, what if I want to graph a whole bunch of points at the same time? You can graph simple things like y equals 2x and whatever, right? So now just like we do that with points in polar form, we can also graph functions in polar form. And so what do these functions look like? So typically what we do, in actually before we even do that example, typically in Cartesian coordinates, we usually do this, right? Y equals f of x, right? In Cartesian coordinates, we do that. That's how we identify functions usually, right? Sometimes there's other ways we do it. But for the most part, that's the way that we identify a function in Cartesian coordinates. In polar form, we do it like this. We say r equals f of theta. And so just think about what that means, right? Like here, when we say y equals f of x, that means that we plug in values for x into the function. And whatever the function is will tell us what the corresponding y value is, right? So basically x is the independent variable. We plug in whatever x's we want. That tells us the corresponding y values, right? In polar form, what's the independent variable now? Well, theta is. And so I will plug in a particular theta value. That theta, when I plug that into whatever function it is, it will spit out a number. That number then is the radius, and it will tell me how far away from the origin I need to be at that particular value of theta, okay? And so you can get nice curves out of this by just varying theta and seeing how the r value changes. So for example, in number 4, we've got some very simple functions. Now thinking again about what a constant function looks like in Cartesian coordinates, right? What does a constant function look like? In other words, if I just said x equals a number or y equals a number, just like one variable, that's it, right? If x equals, I don't know, say 2, that's like a vertical line, right? We know what that looks like. It's a vertical line. If I say y equals 3, we know what that looks like. It's horizontal line, right? That's what the constant, if you just have one variable equal to a number. What about it in polar form? What if you have just one variable equal to a number? What does that look like? Well, just as with these, like if x equals 2, that just means that there is no restriction at all placed on y, right? So as long as x is 2, that's what produces that vertical line. Y can be anything, right? And then if y is 3, well, then that means x can be anything. And so that's where you get that horizontal line. X can be any value. Very similar here. When I say that theta is equal to pi over 3, that just allows r to be any value possible, any possible value for r. And so all that has to happen when you graph this is that theta just has to be pi over 3. That's it. So when theta is pi over 3, that's kind of like this. You see what I'm doing there? I'm just drawing a line. Because if you think about it, the angle there is pi over 3, you see? And as long as I just make sure that angle is pi over 3, then any point that lies on this line is going to have that theta being pi over 3, you see? And so when you see a constant theta in polar form, what is it? It's a line through the origin, okay? It's a line through the origin. That's what a constant theta means, okay? What about a constant r? What about when you have the other function being constant, the other variable being constant? So in this case, if r is constant, again, that means that theta can be whatever. Theta can take on any value. But as long as r is equal to 3, then you're good. Then it satisfies that equation, right? And so what is that going to look like if r is constantly 3, but theta can be anything you want it to be? Very nice graph of a circle. Exactly, that's a circle. And that actually brings us to like, why do we care about polar form? Why do we care about polar coordinates? Why would we even invent these coordinates? Well, it really has to do with functions that are better represented by circular things, or even anything that even has some kind of a circular shape. Because if you look at this, that's a constant function in polar form, right? And it produces a circle. Well, what is a circle? What does it take to produce a circle in Cartesian coordinates, right? A circle in Cartesian coordinates is a pretty complicated thing, right? It's x squared plus y squared is equal to r squared. That's kind of complicated, right? I mean, if you want to actually treat it as a function, you actually really need two functions, right? You would have to have y is equal to plus or minus the square root of r squared minus x squared. That's not a really nice function to be working with, right? What's much nicer to work with than that complicated thing? A constant function is, right? And so circles in polar form, circles centered at the origin, are constant functions, okay? Yeah, in fact, if you're talking about, if you're trying to do any sort of orbital mechanics or map, figure out what the trajectory of something in orbit is, you would definitely be better off doing that in polar coordinates than you would in rectangular coordinates. In fact, if you go on and take some physics classes when you're talking about mechanics and stuff like that, or anytime you've got, the two-body problem of things orbiting each other or something like that, polar coordinates will work much better with that. So yeah, this is one reason why we kind of like to use them. And putting functions that have, stuff orbiting around something else, they're much nicer put into polar form usually. All right, so that's what they look like when you have a constant function. What if you don't have a constant function? Let's take a look at example 5. So that one's clearly not a constant function, it's something else. It's got both r's and thetas in it, right? But it's still a pretty simple function, and you can get a pretty good picture of what it's going to look like. R equals 5 cosine theta. And again, just like when we first started graphing functions, again, you got to kind of think back to your earliest math classes when you started talking about algebra or geometry, graphing anything, right? And you were first learning how to graph some function, you didn't know what it was going to look like, you would make a table, right? And then that's what we did with the parametric ones, right? We had that third column there as well. Make a table, pick some x values, find the corresponding y values, plot all those points. That gives you a pretty good picture of what the function is going to look like. And so here we're going to do the same thing, since it's kind of hard to tell what this is going to look like by just looking r equals 5 cosine theta. Okay, great. What does that actually look like? So the way we do that, again, is we pick values. Now in this case, we're going to pick theta values and see what the corresponding r values are. So what are good values of theta to choose here? Well, probably all the ones that we use on the unit circle, the quadrantal ones, 0, pi over 2, pi, 3 pi over 2, and maybe 2 pi. And if you wanted to, you could also fill in some other ones, put like pi over 4 in there, 3 pi over 4, stuff like that. So if theta is 0, right? So plug in 0 there. Cosine of 0 is 1, right? So that's going to give me an r value of 5. What about pi over 2? What's the cosine of pi over 2? It's 0, right? And so that's going to produce an r value of 0. Pi, when I plug in, when I take the cosine of pi, it's -1, so I'm going to have a -5 there. 3 pi over 2, it's going to go back to 0. And then finally for 2 pi, it's going to be back to 5 again. And so to graph this thing, what do I need to do? Well, let's see. When r is 0, I'm going to go out to 5. So 1, 2, 3, 4, 5. I'll just put a point right there. That's a point that's on our table, right? R is 5, theta is 0 radians. Now, when I plug in pi over 2, that's straight up. So in other words, if I'm pointing in that direction, my radius is 0, I'm actually going to be right at the origin there. And if you were interested, if you put pi over 4 in there, you would find pi over 4, right? Pi over 4 is like root 2 over 2 for that cosine. It's like 0.7, so it's going to be about 0.70% of what it was when we were at 0. So 0.7 is going to be, well, 7/10, or I'm going to try to eyeball it. It's probably going to be about right there. If I was pointing at pi over 4, right, that direction there, my radius would be about right there. And then if you were to do the same thing on 3 pi over 4, which I didn't put on there either, but you would also find a similar situation. In fact, eventually you're going to find that point is also on the graph. And if you kind of put all this together, what you're going to find is that it produces this type of graph, and that is a circle. So in polar form, r equals a number cosine theta, or a number sine theta for that matter. Those are going to produce circles. Now I want to show you one other thing on your graphing calculator. Just like we had in parametric equations, we also have polar graphing on our calculators. So let me share my calculator app again, and then I'll show you how to do that. And as somebody noticed also, that Desmos has a polar form as well. So we can look at that too. But if you have a graphing calculator, I do want to show you how this is going to work. Okay, so there it is. If you have your calculator, go ahead and follow along with this. Same way that we were going into polar form, you're going to go second. Oh, I'm sorry, you're going to go to mode first. We got to do mode first. Then go to, see how in parametric we have the PAR, POL, polar form. Put it in polar form. And then when we go to y equals now, you'll see that it looks different again, right? This doesn't look the same as it did in parametric. It doesn't look the same as it did in Cartesian, right? So what are we going to enter here? Let's just enter that same function, 5 cosine theta. So 5 cosine. Now when you push that x, t, theta, n button, it automatically becomes theta here. So you push that, entered the function. Now we do want to change the window as well on these ones. So if you want to graph a full circle going from 0 to 2 pi is a good way to do that. The theta step, again, that's the same thing as that step value that we were talking about with the parametric ones, with the t value, t step. Making it too big makes the graph kind of jagged, making it too small makes it take a long time to graph it. The x and y stuff, that's just what you're actually going to see on the xy plane. So if we look at what we graphed on by hand here, it seems that x min is probably good to be -1. X max, let's see, it goes out to 5, so going out to 6 is probably okay. Yeah, these are all good, it seems already, so I'm just going to graph it, and boom, there it is. You see, just like we saw by hand, only a little nicer looking. And notice it doesn't quite look circular there. If you want it to look actually like it's supposed to look, there's this zoom here. If you go to zoom square, the 5th one on there, that will force it to be an aspect ratio such that whatever the shape of the graph actually is, it will be true. So if you push that, you can see it definitely is a circle. That produces the actual aspect ratio. In other words, the width of the x is exactly the same as the width of the y. Tick marks. All right, so in the previous section, they kind of, when they were talking about parametric equations, they split the intro to parametric equations into one section and then the calculus of that into a different section. In this polar stuff, they decided they wanted to just put the the calculus stuff in the exact same section, or some of it anyway. So the tangents to polar curves are in this section, but then the integral calculus stuff with polar coordinates is in the next section. So let's take a look at the derivative calculus of the polar form. Again, this is the idea here, is that we're still graphing it on the Cartesian coordinate system, right? We're still graphing everything with the x-axis and the y-axis. We're sort of overlaying this other system on top of that, right? This polar coordinate system right on top of the xy plane. And so what we have to do here is kind of view that theta is now going to be a parameter here. And what we have is, if we remember, we have x is equal to r cosine theta. This is the conversions, right? X is equal to r cosine theta. But what we have to kind of view here is, it says it right there in the tangents to polar curves section. What we have to view here is that theta is the parameter now. It's almost like parametric equations. In fact, it really is. And so if we do that, then we realize that r is itself a function of theta. R equals f of theta. And we do the same thing for y. Y is equal to r sine theta. And that there's some other, or sorry, it's the same r, right? So this we could view as f of theta sine theta. And so with that in mind, if we view this as a parameter, then we can actually use that parametric formula for finding a derivative. And what was that formula? It was that we have dy dt, but here we're viewing theta as the parameter, so it actually is dy d theta over dx d theta. Now, what is dy d theta? Notice up here, if this is y, on the right side of that, I've got product, right? I've got a product. Or if you just might view it like that. So unfortunately, we have to use the product rule to find that derivative, dy d theta. The two parts of that product are the r and the sine theta. Okay, I'm not going to bother with the f of theta there. But we do have to view this as a product, and so therefore we have to use the product rule. The product rule says to take the derivative of the first function. But again, since r is a function of theta, its derivative has to be dr d theta. So derivative of the first function times the second, plus the first function times the derivative of the second. So there's the r cosine theta. And then in the denominator, very similar anyway, with the x, again, we were seeing kind of a product of two functions. There's the r and there's the cosine theta. And so there, for derivative of the first function, again, is dr d theta, multiplied by the second, and then plus the first function times the derivative of the second. The derivative of cosine is negative sine, so that actually changes that denominator to negative. So this formula is a bit complicated, and it's really not that nice to work with, unfortunately. So using that, you could answer a question like number 6. It says, find the slope of the tangent line at the given value of theta. So suppose I have a function here, r equals 2 plus sine 3 theta, and I want to find the slope of the tangent line at this particular value of theta. So again, this is graphically speaking, so I would be looking at the xy coordinate system, and so I have to be thinking about what is dy dx. That's the only thing that's going to show me physically what the tangent line is actually going to look like. And so to find that, I need, well, let's see, I need dr d theta, right? What's dr d theta? It's going to be 3 cosine 3 theta. I'm just looking at the derivative of that thing. The derivative of 2 is just 0, and then the derivative of sine 3 theta is 3 cosine theta, 3 cosine 3 theta, sorry. And so putting all that stuff in, I'm going to have dr d theta, so that's 3 cosine 3 theta. Then I need a sine theta plus r, but r is actually this, 2 plus sine 3 theta, cosine theta. And then the denominator, very similar, 3 cosine 3 theta, cosine theta, minus r again, 2 plus sine 3 theta, and then we need a sine theta there. Okay, everybody see what I'm doing? I'm just plugging it into this formula. That's it. Where dr d theta is that quantity there, and r, whenever I see an r, I just replace it with that. And so if I want to find the slope of the tangent line at this particular value of theta, unfortunately, what do we have to do? We got to plug the theta into all of that mess. So we'll do that. So what is dy dx when theta is equal to pi over 4? So we got to plug that in. So 3 cosine, if I plug pi over 4, I'm going to get 3 pi over 4 there, right? 3 pi over 4. Sine pi over 4 plus 2 plus sine, that's going to be 3 pi over 4 again, right? 3 pi over 4 there. Cosine pi over 4, all this divided by, that is going to be the same as the denominator, sorry, as the numerator there, except this is going to be a cosine now, so cosine pi over 4. We'll go back and figure out what all these are, and then the sine of pi over 4. Okay, so putting all this together, evaluating it, the cosine of 3 pi over 4 is, what is that, negative root 2 over 2. The sine of pi over 4 is positive root 2 over 2. Then we'll have plus, let's see, that's going to be 2 plus the sine of 3 pi over 4, which is root 2 over 2 again. Cosine of pi over 4 is another root 2 over 2. A lot of root 2 over 2's in here. All this divided by, same thing here. Cosine pi over 4 is also the same, root 2 over 2. And then all of this is the same as well. Yeah, so a big mess there, and then we just got to simplify that a little bit further. It's going to be numerator. What is that going to be? The root 2's cancel there, right? Root 2 times root 2 is 2. It looks like we're going to get negative 3 halves to start with there. Negative 3 over 2. The next one will have plus root 2, the next term, distributing, and then plus 1/2, I guess. And then the denominator will get, that's going to be exactly the same, so negative 3 halves minus, and then that's exactly the same. Okay, and then combining this stuff, looks like we get, let's see, minus 3 over 2 plus 1, so it's minus 2 over 2, so minus 1, right? So we'll get root 2 minus 1. The denominator will get minus 3 minus, it's minus 4 over 2, so minus 2. Minus root 2 minus 2 there. So here's all Michael's work for 10.3. There's only 2 problems on there, so you can kind of see it's a lot of this, like finding the slope of the tangent line for these is really more just tedious than anything else, as you saw in the example. Like, what do you got to do? You got to use that kind of crazy formula here to take that derivative. That's what's happening at the top there. I didn't realize that simplified to be just tangent. Oh yeah, it does. That's crazy. That's kind of cool. Did it do that though? What happened on that?
On which one? Problem 1?
Yeah.
Yeah, that was the slope. So I think that's all it was asking us for.
How does it end up being just tangent there though?
Let's see. We got, oh, so -2 sine 2 theta cancels on top and bottom, leaving only a sine and a cosine.
-2 sine 2 theta.
It's on the second line.
Well, where does the r cosine theta and r sine theta go?
Let's see. Oh, okay. So when we put that theta in there, into the r equals cosine 2 theta, we end up with r equals the cosine of pi over 2, which is 0.
Oh, I see. So they go only in that particular angle for theta. Okay.
Right.
Oh, I see. Okay, so it doesn't normally happen. Just in this case, that's what's happening. Okay. All right, cool. So yeah, just keep that in mind for that particular angle that they're giving us. Those two terms are going away. And then yeah, so for the rest of it, you just have to plug in the given value for theta. That's it. So yeah, you just end up with a 1 there. That's kind of nice. And then for the second one, yeah, that one's really long, I guess.
That second page there on the second one was to clarify an issue that came up with the horizontal and the vertical. They both came up with the answer in common, and I had to decide which way it was going.
Yeah, that's a good idea because it's important that people do understand this particular problem. When they're asking for where the tangent line is horizontal, what does that mean? That means where the derivative is equal to 0, okay? So what Michael is doing there is taking the derivative and setting it equal to 0 and solving for it. Yeah, that's what he's doing here. He's taking the derivative and setting it equal to 0 and getting a couple of places where the cosine is equal to 0 right here and right here. That gives you 3 different angles basically on the unit circle where this thing is going to have a horizontal tangent line, okay? So that's where the derivative is equal to 0, setting it equal to 0 and solving, okay? Now, a vertical tangent line, what is a vertical tangent line? That's where the derivative doesn't exist. So how do you determine that? Well, that's where the denominator of the function, the derivative, is going to be equal to 0. Okay, so the first one that Michael did here was setting the numerator equal to 0. That's this, right? You can see numerator equals to 0, right? When you want to find the vertical tangent lines, set that equal to 0 for the vertical ones. And so that's what's happening here. Numerator to 0 for horizontal tangent lines, denominator to 0 for vertical tangent lines. Okay. Is that clear? And then the stuff about the plus 2 pi k, this is just to getting all of the possible solutions everywhere, but even outside of the unit circle. So basically, you take any answer that you got from solving the trig equation, add plus 2 pi k to it. That allows you to get all possible solutions. And then this is setting the denominator to 0. You see right here, that's what he did. And solving that, you actually get really just 3, right? 0, pi. But I think, didn't we find something funny on this one, Michael? Like,
yeah, pi came up as a solution to both the horizontal and the vertical.
Right. Yeah, so you see pi is here and it's also here. It's a solution to both. What that actually ends up meaning is that's just a place where the derivative doesn't exist at all, okay? And so there's no vertical tangent line there, there's no horizontal tangent line. It's just that, in fact, if you look at the graph, if you were to graph this thing on the calculator, what you would find is that actually happens right there is this sort of thing. You're going to see that, like a point on it, a sharp point. So that's not a horizontal or a vertical tangent line. So kind of what you have to do on these problems is compare the answers that you get for vertical to the ones that you get for horizontal. If you get a single answer that occurs in both, that means you're going to have this situation here, like a sharp point situation. Any solutions that only occur on one or the other, like these ones here, right, that's only on the numerator to 0. That's a horizontal tangent line. These other ones here only occurred for the denominator being 0. So those ones those do count. Those would be vertical tangent lines. Okay.